All right, so let's look at this example of female black bears in California. You can see here we got a picture of a black bear, and this is the outline of the state of California. And the area that I've shaded in gray, this is, the general habitat, sorry, left where you can find black bears. And what we're going to be doing is we're going to be sampling um, black bears, trapping them, measuring them in each of these locations in their habitat, denoted by a triangle. So this problem says, or this example says, the distribution of the weight of female black bears in California is unknown, but measurements indicate a mean of 175 pounds and a standard deviation of 50 pounds. From each sample site in the state, samples of size 16 are drawn randomly from the population. What is the probability the sample mean from a site is between 170 and 180 pounds? So to answer this question, we're going to answer it in four different parts: A, B, C, and D. Question 2 is to find the value that is 2 standard deviations above the expected value of 175 of the sample mean. All right, so there's kind of a lot going on with this problem. So let's try and identify all these different parts. All right, so it says the distribution of the weight of female black bears in California is unknown. All right, so what does this mean? So when it says the distribution, remember distribution means shape. So if we were to take every single female black bear in California, every single one in that gray area, and weigh every female black bear, and then we were to graph like a dot plot, of that, um, what shape would that take? Would that take, like a normal distribution shape? Would it take, like a uniform distribution shape? Um, this is like what we had in chapter 5. This was chapter 6. Would we have a distribution shape that was maybe, exponential, something like that? We don't know. Okay. But for the central limit theorem to work, we don't need to know. So the fact that we don't know what the distribution of female black bear weights in the population are isn't going to matter for the central limit theorem. All right, so it says, but the measurements indicate a mean of 175 and a standard deviation of 50 pounds. So this mean and this standard deviation, this is in regards to the weight of all female black bears in California. Now, it doesn't have the word all, but I think you can see it's somewhat implied here. So that means in this shaded region, if you were to measure the weight of every single female black bear in this shaded area, they're going to have a mean of 175 pounds and a population standard deviation of 50 pounds. All right, so that's kind of what we're looking at there. Now it says from each sample site in the state. So the sample site is what's been denoted as a triangle here. That's our sampling site. And we've got these sampling sites located in the black bear habitat in California. Samples of size 16 are drawn randomly from the population. So at each site, we are trapping 16 bears. So from each site, we have a sample size of 16. something like this. Okay. Question is, what is the probability the sample mean from a site is between 170 and 180 pounds? All right, so what is this talking about right here? And let me use a different color for that. All right, so what does that mean? So at each of these sampling sites, we're going to be calculating, we can calculate a sample mean. So the mean of this sample is some number. Here is our second sample. So that'll give us a second sample mean. Here is our third sample. So this is going to give us our third sample mean. Here is our fourth sample. So this will give us our fourth sample mean, and so on. So the question is, what is the probability the sample mean from a site is between 170 and 180 pounds? So what we want to know is what's the probability that a sample mean is between 170 and 180 pounds? That's what we want to know. Now, what separates this chapter from previous chapters, like in chapter 6, for example, we would have been interested in knowing what was the probability that a single bear had a weight between 180 and 170, right? This small lowercase x represents the weight of a single bear. So what's the probability that the weight of a single bear is between 170 and 180? What we're asking now is not the weight of a single bear, but the mean of a single sample. So what's the probability? Oops, I'm sorry. What's the probability that a sample mean from any one of these sampling sites is going to be between 170 and 180? Because we're going to be dealing with a distribution not of bear weights, but we're going to be dealing with a distribution of averages, of means. So we're going to have, let's see if we can take that out for now. So we're going to be taking all of these sample means, and if we were to make like a dot plot of them, it's going to look like a normal distribution. So this is our distribution of sample means. And that's kind of the quote beauty of the central limit theorem, is that it doesn't matter what the distribution of the random variable is. So in this case, the weight of black bears, female black bears, it doesn't matter what shape that takes. If we were to take the mean of every single sampling site and we were to graph all of those means, the graph of those means will be normal, will be a normal distribution, regardless of what the original data was. Because now we're talking about not the shape of weights, but now we're looking at the shape of averages, the shape of means. And the shape of means is normally distributed. Okay. So that's kind of what we're dealing with here in chapter 7 with the central limit theorem of means, of sample means. So in order to answer this question, all right, to help you kind of further develop the idea of this section, we're going to kind of break down the answer into these different parts. Okay, so let's look at these different parts. So part A is to define the random variable x literally and in notation form. So random variable, so we're going to label this as a capital X. This is going to be composed of the weights of female black bears in California. And to put this in notation form is where you do something like that. Okay. So this random variable, this is, so we put kind of like a little squiggly line. And then the next letter denotes the shape of the distribution. Now remember, we don't know what the shape is for the weights of female black bears in California. We don't know. We don't know if it's exponential, uniform, or normal. So I'm just going to put a question mark there for that. But we do know that the mean weight of female black bears in California is 175. And the standard deviation is 50. All right. So here we've defined the random variable X literally. That means we've used like a sentence or words. And we've also represented this in notation form, which looks something like that. Okay, so now define the sampling distribution of the mean. So we defined what our random variable X was. What is random variable capital X bar? Okay, so here, capital X, the random variable capital X represented the weight of bears. Over here, capital X bar is going to represent the averages, the means of each sampling site. So this is going to be means of samples in California of size 16. All right, so this random variable is composed of averages. It's composed of means. The previous one was composed of individual weights of bears. Now this next one is composed of a bunch of averages. Okay, part C. Write the question in the form of the probability of an event. So I kind of did that above, but I'll do this again. What's the probability that the mean weight at a sampling site is going to be between 170 and 180 pounds? Okay. Now let's go to the next part, part D, is we want to visualize the problem. Oops. Let me erase this. Oh. All right, let me pause the video here for a second. Okay, so somehow this picture in my lecture notes got changed out. So I just changed it back in. All right, sorry about that. All right, part D is to visualize the problem with a picture of a normal distribution. So the reason why now we're drawing a normal distribution is because that's how the distribution of sample means looks like. Okay. So this is what the distribution of sample means will look like. It'll be normally distributed. So just going to sketch a normal distribution as best as we can do it. Doesn't have to be perfect, but we have to know what we're doing. Okay. And let's see here. What are our givens? So we know that the population mean is 175. We know the population standard deviation is 50. And we know the sample size at each sampling site is 16. So this means that the center of our normal distribution is going to be 175. So again, I just made a little bit of a jump, and let me explain what I did. So what we're drawing here is we're actually drawing this capital X bar distribution, which means that the center of it is going to be the mean of those means. Okay. Well, when it comes to the central limit theorem, the mean of those sample means is going to be equal to the mean of the population. So if the mean of our population is 175, so if the mean of our population is 175, then so will be the mean of our sampling distribution, the mean of this curve. Okay. So these two, quantities here are actually going to be the same number. All right. Now, what we're being tasked with finding is we're being tasked with finding the, let's see, where can I put that? The probability that a sample mean is between 170 and 180. So here we have our distribution of sample means. So we want to find the area between 170, okay, to the left, and 180 to the right. So what we're looking for is this area. So we want the area between 170 and 180 of this normal distribution. All right, so if you're using the Texas Instruments or the NumWorks calculator, let's start to put in a few values, and that'll kind of lead us to what we need to do next. Okay, let's go ahead and plug in what we've got. So for the Texas Instruments calculator, okay, our lower number is going to be 170. Again, we're using the normal CDF function because we're taking values of X and we want to convert those into an area. Okay. All right, so the lower number is 170. The upper number is 180. Get that up here. Okay. The mean is 175. So what's the standard deviation? You might be tempted to say, oh, the standard deviation, they gave it to us. But remember that this is the standard deviation of the weights of black bears, not the averages of weights of black bears. All right. Now, when it came to not standard deviations, when it came to means, we could say that the mean of the sampling distribution of means is equal to the population mean. We could do that. All right, but what we cannot do is we can't do the same thing with the standard deviation of the population and the standard deviation of the distribution of sample means. Those are not equal, at least not equivalent this way. All right, so this value of sigma that we want, we don't want this one. We want this one. And the reason we want this one is because this one actually relates to this graph, to this normal distribution. Because remember, this is a distribution of sample means. And the relationship that we've got, in order to calculate the standard deviation for the distribution of sample means, that's equal to the standard deviation of our population divided by the square root of 12. And so the standard deviation of our population was 50. I'm sorry, this wasn't 12, it was 16. Sorry. And the square root of 16 is 4. So this is going to give us a standard deviation of our distribution of sample means of 12.5. And it's this value of 12.5 that we get to put there. Okay, so just be forewarned, had you put in 50, it would have been the wrong answer. Okay, had you put in 50 in this spot, it would have been the wrong answer. And for the NumWorks calculator, we would have a mean of 175. Okay. The standard deviation, again, we would have had to have realized at that point that we couldn't use 50 and that we would have to put 12.5 in there. And we want the area in the middle between 170 and 180. And when you hit enter, that would give you the area in that spot. And here for the Texas Instruments, you'd have to hit paste and then hit enter again in order to run the normal CDF function and get the area. And what you would end up getting then is that the probability that the sample mean at a sampling site would be between 170 and 180 pounds is equal to 0.3108 or 31.808%. All right. And so that's what this area, 0.3108, that's this area right here between 170 and 180. All right, now let's look at the last question. Question 2 is find the value 2 standard deviations above the expected value. All right, so what are we looking at here? So I'm going to draw a normal distribution. This is for our distribution of sample means. We know that the center of this is 175, and we know that this also has a standard deviation of 12.5. So there's a couple ways to go about it. We could take 175 and go 2 standard deviations to the right, adding 12.5 twice, which is going to be 25, right? That's the same as just adding 25 in one fell swoop. And adding 25 to 175 is 200. So our answer is going to be 200. Or we could look at the algebraic equivalence in that our sample mean, that's 2 standard deviations above the mean, is going to be equal to the standard deviation of our distribution of sample means times the z-score plus the mean of the distribution of sample means. This quantity we calculated to be 12.5. We want 2 standard deviations above. So that's going to be a positive 2. And that's going to be plus 175. 12.5 times 2 is 25. plus 175. So that means that the mean, the value that is 2 standard deviations above our mean of the sampling distribution is going to be 200. All right, so here I answered this question using this algebraic relationship. Okay, which is the same relationship that we learned back when we learned about z-scores, converting back and forth into z-scores. Just the terminology just changed a little bit here. Or we could have just solved this simply by drawing the graph and thinking of it in this way in order to get to 200 from 175. All right, so that concludes this example. Let me know if you have any questions.